Over the course of the last 26 years, we have observed over 4,700 exoplanets, some similar to Earth and others not so much. Nonetheless, we have still opened the possibility of a home away from home if something happens that forces us off of the Earth and to the stars. The Earth Similarity Index, or ESI, is a formula created to easily measure the similarity of other planets to Earth. The scale works by replacing the variables of the equation with information about the planet, and when it is calculated, the result will have a number between 0 and 1, 0 being not Earth-like whatsoever, and 1 practically being Earth 2.0. For a sense of scale of the ESI, Mars sits at a 0.7, Venus at a 0.44, and Jupiter at a 0.12. 12 light-years away, we find ourselves on Teegarden-b, which scores a 0.95 on the ESI. The world orbits a red dwarf star, and its orbital radius is only 0.02 astronomical units, placing it very close to the star. Even with its short orbit, it still remains in the inner edge of its habitable zone. Although being so close to the star, the planet has a chance of undergoing extreme greenhouse gassing, similar to what happened to Venus billions of years ago. Many red dwarf stars are classified as flare stars, meaning they spontaneously shoot out massive solar flares capable of ripping away planets' atmospheres. Luckily though for Teegarden-b, its star has been observed to be very quiet, and very rarely has massive solar flares that can ruin a planet's habitability. Something else to look out for is because of its orbit, the planet may be tidally locked, meaning one side of it permanently faces toward the star and the other permanently away, similarly to how our moon orbits the Earth. A planet being tidally locked can cause some complications with its habitability, though it is not a death sentence. The main problem is that without anything like an atmosphere to dissipate the heat evenly, the side of a tidally locked planet facing away from the star is extremely cold, while the side facing towards it can be extremely hot. But an atmosphere thick enough would make temperatures safe on both sides. A planet's composition is determined very soon after its formation around its star, and many terrestrial or rocky planets will pick up water as they come together. Whether or not the water remains on the surface depends if the planet is in its star's habitable zone, but not all planets equally receive water upon formation. Some planets get almost no water, creating dry, arid deserts where almost nothing can live on the surface. Some get small amounts of water, making muddy worlds that don't have enough water for oceans, but instead regularly dry and wet spots on the surface, allowing for microbes to thrive and live in the wet areas, as well as swapping seasons for the expansion and retraction of permafrost moving out from the poles. Other planets are lucky and have a good mix of water and land, much like we have here on Earth. And finally, some planets like Kepler 22b receive much more water than here on Earth. The oceans on this world fully cover the planet's surface and can be several miles deep at their shallowest. The key for life on an ocean world like Kepler 22 would be buoyancy, where life would try to remain as still as possible to not use up any of the very little energy available to it. 20 light-years away, we look at gliese 581g, which scores a 0.92 on the ESI. This world orbits a red dwarf star located in the constellation Libra. The planet is 7th in orbit of its star, though remains the only one safely in its habitable zone. Its star is very inactive, similarly to Teegarden's star, and the planet is almost 3 times as massive as ours, giving it the title of a super-Earth, which is any terrestrial planet more massive than the Earth. The kind of light our sun gives off is best absorbed with the color green, which is why much of the plant life on Earth sticks to that color. But gliese 581 bathes its planets in infrared light, making the planet very dark on the surface, opening the possibility of strange dark-colored plant life living and thriving, similar to the black mondo grass that we have on Earth. In fact, since most stars in the universe are red dwarfs, plant life like what we have here on Earth may be uncommon, and instead red and black plants may be normal on alien worlds. Moving on, we find ourselves in the TRAPPIST-1 system, or what is possibly the greatest discovery in habitable exoplanet history. The TRAPPIST-1 star system has 7 rocky Earth-like worlds orbiting it, and 3 of which are in the habitable zone. Its star is an ultra-cool, inactive red dwarf star with a radius slightly larger than that of Jupiter, and all 7 worlds orbit within the distance of Mercury to our own sun, in other words, within 9.2 million kilometers. The TRAPPIST planets are named TRAPPIST-1 b, c, d, e, f, g, and h, in that order of distance from their star, and are all probably tidally locked. TRAPPIST-1 b and c sit too close to the star and would be too hot for any life to emerge. They would be more comparable to Venus than Earth, while TRAPPIST-1G and H sit both too far from the star and past its snow line, meaning any potential water on the surface is probably frozen under an ice sheet. However, TRAPPIST-1D, E, and F all sit in its star's habitable zone. TRAPPIST-1D is a small Mars-like planet sitting in the inner edge of the habitable zone. It has 1/3 of the mass and about 2/3 of the radius of the Earth. Because of its size, it likely has very little water on the surface and very little atmosphere, though the temperature may stay close to Earth's at roughly 9 degrees Celsius. TRAPPIST-1F sits on the outer edge of the habitable zone, though water still may exist on the surface. It has roughly 2/3 of the mass of the Earth and is almost the same size as the Earth, though slightly larger. Simulations suggest that the planet's mass is 20% water in comparison to the Earth's 0.02%, possibly making it an ocean world like Kepler 22b. TRAPPIST-1E sits square in the middle of the habitable zone. It has 70% of Earth's mass and roughly 90 to 95 of the radius. Its temperature may be very Earth-like if its atmosphere is anything similar to ours. TRAPPIST-1E also has a very similar water-to-rock density to Earth, meaning it probably has the land and water combination similar to how we do. Plugging all of the statistics of TRAPPIST-1E into the ESI equation, it comes out at a 0.96, and is the highest we have ever observed. The TRAPPIST system is probably our best chance if we have to escape for any reason, and while 0.96 is quite high on the ESI, nothing can compare to the 1.0 we have on Earth. We need to take better care of the only home we have before it pushes us away and we are never able to go back.